We're going to dive in today about how to analyze data. So you've spent the last couple of days reviewing some things with prior knowledge for statistics and data. And so just some things to go over first is when we look at different types of data, there's all different ways that it can be shown. What we're going to be working with most is histograms. And a lot of times what people will mix up is bar graphs and histograms. So I want to talk a little bit about the difference. So a bar graph is categorical data. That means at the bottom or the x-axis, the independent variables are individual things like your favorite kind of ice cream or your favorite car or your most favorite movie or your best vacation spot. And this particular one here, we have largest companies of 2019 by revenue. So these down here are company names, Walmart, Best Buy, so forth like that. So on our y-axis, we have frequency, how often. So this is always a frequency here on the y-axis. We have our frequency, but these are individual categories. Notice that there's a gap between the bars. These are very good to be used for a quick comparison. You can easily see what's the most. It shows relative size, but these are comparing different categories. They can write these or make them as horizontal. So you can see that the categories are on the side and the frequencies on the bottom. Notice that they have labels for the x and y axis and always a title for any graph, and they're telling you what the scale is if it's not 1-to-1, that every one of these units represents 5 students, and so forth. So these are examples of bar graphs. So remember, they have multiple different variables or categories, and they're categorical data, different categories. A histogram, however, is not the same. Now, occasionally you will find some histograms that have gaps in between the bars, and that's not a proper histogram. But histograms are the y-axis is still frequency, just like the bar graphs, but the x-axis are in intervals or classes. So it's a range of situations. So 0 to 5, then 6 to 10, 11 to 15, 16 to 20, and so forth. Notice that each of these are the same amount. So we don't have one that's got a span of 10 numbers and the other one's only got a span of 3. They're broken down the same amount of intervals. Another name for intervals could be class. They could say these are different classes, but it's a range of numbers. They have to be the same as far as how much it represents. Each little section has to be representing the same number of interval or space, and it has to be constant. So we wouldn't start at, let's say, 5 and go to 10, and then 11 and go to 20, and then skip and go from 30 to 40. That would be all messed up. We would not do that. So then we look and see, okay, we know the difference. We got categorical or bars, and then for our histograms, these are quantitative. Quantity meaning numbers, numerical, quantitative. So we're talking about numbers of things. Notice this whole thing is about M&M's as a favorite candy, and then they literally surveyed people in different age groups based on that. So we could look at this and say, oh, well, the most popular age group that loves M&M's, their favorite, is 16 to 20. That's the highest amount. All right, you occasionally see some histograms that have overlapping data. So it'll be like 0 to 1, 1 to 2, 2 to 3. For example, this one here, 35 to 50, 50 to 65, and so forth. These are not the best way to do a histogram because it's unclear of if this data is being counted twice in the 50 range, or if it was 49.9, it should go up to 50 and then start at 51. So you have to kind of be clear about what you're doing there. So those are not always the best, but they're used in math a lot. All right, so here's a little bit more about the differences in a kind of one-stop shop. Bar graphs, they have equal spaces in between. We see here the y-axis, we have numbers, which is our frequency, and the x-axis we have data, which we know is categorical data. So this is like class 1, 2, 3, so forth. Whereas a histogram, the bars are fixed. There's not spaces between them. The y-axis, we again have numbers or frequency. And on the x-axis, we have continuous numbers as well. So our number starts. We have ranges and intervals of class between those intervals there. So some things you have to be able to do is to talk about data in a very specific way. So we're going to talk a little bit about the different ways to talk about data. So statistically, when you're looking at distribution of data, how it's distributed or how it looks on a graph and a histogram, we use the look of shape. So this is a normal symmetrical shape. If these were bars, you could kind of think about these as bars, and they are perfectly normal. And notice we have one peak, and then it comes back down, okay? This is what we would consider a symmetrical unimodal. So it's got one peak here. That means one modal. It's bell-shaped, a bell-shaped curve. This having a tail doesn't really matter right now for your level. Notice that in the middle where this dotted line is right where the peak is. That is where your mean, median, and mode all reside. They all gather right here at the peak. So that kind of splits the data 50-50. We actually use this to see if you pass the EOC. So everybody takes the EOC, all the grades get put into like a histogram, they draw a shape over it. That top peak there, those people, and so much, obviously all these people pass, and then so much of these people pass and these people don't. So this is something that's used a lot in data collection. You want most all data should fall very symmetrical and normal if it's a good enough sample that's been collected. When we go and survey only 10 people and we try to make a generalized statement for the whole population, that's not a good data collection process. So we need enough data. Usually that's about 30 data points to get a good sampling. That's not a good population sampling, but it's a good sampling to start to kind of get an idea in general. So normal is what we'd like to have. Unimodal means one little peak. Mean, median, mode all being there. We also can have a situation where it's flat. So if we try to draw a bell curve here, there's no point. It's like a box. These are all flat, right, straight across. So this is what we call uniform or flat data. Okay, wouldn't be very helpful to see this, that everybody's pretty much the same thing. It's like saying if we were asking certain age groups if they liked M&Ms, and every single one of them said it was a favorite. Did we go to the M&M support group or something and get our data? So where we collected our data from, you start checking like how is this data like that? So you start questioning things when you see data like this. Then we have right skewed, which you should have heard before. So right skewed data is when we put our data in and we kind of have a tail that goes to the right. That means if we have some bars, they come up here and then they start kind of going off to the side and they lean out like a tail. So this is right skewed, which means it's positive skewed because you think of a number line. These are going positive. This way is going negative, so the way the tail's hanging out is positive. If we have something way over here, we could have data up to here, and then no data, and then a point way over here. We know those are outliers. So that's a good portion away from the rest of the data, and we'll talk a little bit more about that in a minute. But I want you to pay attention to where your mean, median, and mode resides in this situation here. So your mean is to the right of the peak. So this is still unimodal, still one little point, a peak there. Our mean is all the way to the right. Our median and what makes our mode is that peak. Our mode is right there at that peak. So this is very important to remember where certain things are there. Our left skewed is another name for negatively skewed. It's just the complete opposite. So it has a tail that goes to the left. So maybe these are grades in a class, and we've got people, making 80, maybe is our most often one. Maybe our median was 78, let's say, and we had a few, 90, 95s and so forth, and 100 maybe up here. But then we had somebody down here that made a 10. So it negatively skewed that data, and it made that mean look lower because if we add somebody that had a 10 average in with a lot of people that had 70s and 80s and 90s, it's going to pull the overall average down. So the mean gets pulled to the left because it's left skewed. Then the median is there, and the mode is always at that peak there. Now, we can look at this in box and whisker plots as well. So I just gave you examples of what a normally distributed box and whisker is. Remember, this is our minimum, our maximum. This in the middle is our median or IQR. From here to here, we have our lower quartile and our upper quartile, or your third quartile. And these are split by 25% in each way of all of our data points. Now, you learned how to make these long ago, so this year it's more of using technology to help you with your data. But you have to know if it looks normally distributed, positive skewed, or negatively skewed. So a box and whisker that's positively skewed, this box is a little bigger, and we've got a whisker sticking out further than the other. Whereas a negative skew, our second quartile area is bigger. Even though this little whisker out here, it's the box that we're looking at, it's bigger, so it's pulling this data this way. Now, let's talk about some different peaks. We have different shapes. We talk about unimodal, that's just the one peak. You can have distribution with two peaks, so we have a peak here and a peak here. You won't see a lot of things like that this year with multiple. You'll see some with bimodal, but that just means bi means two, so two different peaks, distinct peaks. And that could be a situation where different age groups, maybe little kids and then older kids, maybe love the same thing at the same time, or maybe older people like to color just like little kids like to color. That's a pastime people use for stress. Maybe that's what caused that peak. This particular one has three peaks, so anything after two we call multi-modal because it's got multiple modes. Okay, think about where your modes reside. It's got multiple modes, so multimodal. All right, so then we have some more technical information here. Center is the symmetrical distribution using the mean, so we've got to talk about how do we find center. So yesterday you talked about central tendency, mean, median, mode. Those are our main central tendencies. So you think about center of kind of where all the information resides. Mean, hopefully you remember what mean, median, mode. If not, you need to review that. For skewed distribution, something that's left skewed or right skewed, for center we're going to use median to explain it, where if it's symmetrical we focus on the mean. Because obviously if it's skewed, it moves the mean either left if it's left skewed or right if it's right skewed. So if it's skewed, we're going to use the median to kind of tell more about what's going on. So if we took a test in class and I had someone or a couple people not take it or take a 0 because they didn't turn it in, and everybody else did very, very well on it, say, 80s and above, if I average those two zeros in, it's going to skew my data. So to report, I would report median to you instead of the mean or the average. I would give you what the median was, so that's a more telling depiction of what really happened, taking away those outliers. So here's some basic things that you have to know about measure of spread. So how things are spread out. Just think about spreading out mayonnaise on a sandwich or peanut butter out. We spread them out. So there's some things that we have to use to talk about spread. So variance is a word that we use to talk about how things vary. So think about the word, the root there, vary. Variance is how data is spread out. One way we tell about that is range. Range is the distance between the maximum and the minimum, or the difference between the maximum and minimum. Interquartile range, the distance between the third and the first quartiles. We do those in box and whiskers. If something is has a narrow spread, it's packed close together, just like a narrow would be. If I went into the hallway and there's a bunch of people, I'm packed close together. It's very narrow for me to get through. Whereas if I walked out into an empty hallway, the data is spread very far out. It's very wide. I can move about. So when things are very narrowly close together, that tells me that the data is probably more correct, or maybe a better situation. Whereas if I ask somebody something and I'm getting ranges going from 0 to 1,000 and I've got stuff spread out all over, I may need to kind of narrow down what question I'm asking or what data I'm collecting. Now, standard deviation is one that you'll use a lot, and there's two different types of standard deviation. One is a population standard deviation, and one is a sample standard deviation. We usually use a sample the most. An example later I'm going to talk about actually uses population, but population is like everybody, whereas a sample is just a small sampling. We don't have enough money as kids, or most researchers don't have enough money to go sample everybody, a large portion of people. So it's considered a sample, 30 or more. Even if I have 100 people I'm sampling, that's still a sample of the whole population. So standard deviation is one that is really reliable to help us tell how the data actually exists and how reliable the data is, or our results are. So this is how spread out the data is from the mean. So let's say we have a mean of 60, and then I have some points that are 40 and 80 or whatever my data, and I put them all in a calculation, and I get a standard deviation of 2. That means every data point's only about 2 away from the mean. That's very good. That's very reliable. It's a lot closer. It's very low. If I have a standard deviation that's like 25, that means every data point I have averages about 25 away from 60. That's very wide spread out data. That's not the greatest. So having a low standard deviation is much more reliable. High one, not very good. Now these things that I have here, these are calculations. When I actually learned how to do this as a student, we had to do them by hand, and they take forever. You're not going to be doing those by hand, but I want you to see kind of what they look like. You don't have to memorize those. We're not going to be using them. We're going to be using some technology to help you with this. So remember that when we're reporting spread, when we're using spread, when reporting the mean as a measure of center, so remember we do the mean when we don't have any skewedness, when things are normal, we use the standard deviation for the spread. So when things are normal, great, beautiful, unimodal, symmetrical, and we use mean, then we use standard deviation. When we report the median, because we have some outliers that we had to ignore, we report the median as a center of measure of center. We're going to use the interquartile range to report our spread. So we're going to use what we call SOCS to describe or summarize a distribution situation. So SOCS means shape, outliers, center, and spread. And remember, an outlier is any value that is 1.5 times from the IQR, interquartile range, above the third quartile or below the first quartile. And you'll see that example in just a minute. So here's an example that I pulled. This is some raw data here. These are plants, and they're using this as population data because it was the whole population of their farm. And they had then made a histogram of plant heights, how they were growing. So we're going to dissect this data. So the first thing we're going to look at is the shape. So if you think about drawing a bell curve over it, you can see that it's unimodal, and we've got something out here that's kind of almost would pull it towards being skewed. However, that's just one point. It's not a whole bunch of points. So then that brings us in to the next one, outliers. So we're going to look at this data and see if that is an outlier. If it's an outlier, then we know this is still symmetrical. We can kind of ignore it, and we know it's still symmetrical. So remember, an outlier is any value that is 1.5 times the interquartile range above the third quartile or below the first quartile. So for this data, I've already calculated our interquartile range from our data is 3. And our third interquartile range is 9. Okay, so we would have to be 3 times 1.5, whatever that equals, added to 9 away. So when I do that calculation, 9 is my third interquartile range. So I'm thinking about right here. And I have, if this point is 1.5 times 3 away from 9, then I know it's or bigger, it's an outlier. So in this case, when I do my calculations, it's 13.5. That means anything from 13.5 on is considered an outlier. Well, he's at 22, so he's definitely an outlier. So we know he's an outlier. So now we can think about, well, we know he's an outlier, so then we know that this is just symmetrical, and it's unimodal, one peak. because we took away that outlier. Then we look at our center. Remember, our center is just like central tendency, mean, median, and mode. I use the calculator to calculate that. I have my mean, median, and mode listed here. Then I look at my spread. Your spread is looking at your range, which we know is the biggest number from the smallest number. It's also looking at your interquartile range, which we already know, our standard deviation, and our variance. Now, our variance is our standard deviation squared, okay? So when we look at this, our range is 18. Our interquartile range is 3. We'd already calculated that for the other one. Our standard deviation is 3.69, and again, they use population, not sample. And we do all this on a calculator or in Desmos. It does it all for you, and you're going to learn how to do that. Variance is just that standard deviation squared, and so we know our variance is here. So how we would report this after we got all that information is we would be able to say this distribution was unimodal and symmetrical. The distribution had an outlier of 22. The distribution had a mean of 7.85, a median of 7, and a mode of 7. The distribution had a range of 18, an interquartile range of 3, a standard deviation of 3.69, and a variance of 13.63. So that's our conclusion for our data if we were having to report it in a technical sense for someone else. Now, we're going to go into detail about how to use the calculator to put in some data, and I'll do a separate little video to kind of show you how to do that. This gives you the written guide so you can work with your data, but we're going to be also using Desmos, which is so much more user-friendly and a lot easier to deal with than the calculator, but you need to know both. I will let you know what some of these mean. So when you're using this, you'll see these little symbols here. So they kind of give you a chart. Mean, obviously, is mean. Sample standard deviation, the SX, is what we normally use for most of our stuff. This particular one that I showed you an example of used the population standard deviation. And then we have our median. Minimum and maximum will help you find your range. Mode, you're going to have to look at your data to see what happens most often. And for your variance, you'll have to take your standard deviation and square it yourself to find it. And then I went into how to make a histogram on your calculator as well. Once you understand Desmos, you'll probably never use this on your calculator, but they are here to help you and to go through, and these are in hard copy form for you to print off if you would like.